Okay, these are the notes on the area between two curves. So what we want to keep an eye on and remember is when we were talking about area under a curve. Here is a graph of the type of notation that we used for that. You're going to see that we're looking at the area from a left endpoint of A to a right endpoint of B, and that we divided that interval up into sub-intervals with endpoints of x sub 1, x sub 2, x sub 3, etc. And what we found is that in between the endpoints of these subintervals, we used a sample point to plug in order to find the height of the rectangle. So then to find the area under a curve, we took the width of a rectangle, which we found by taking the length of the interval, which is b minus a, and dividing it up into n rectangles. And sometimes that was a specific number. If we were approximating area under a curve, for example, that would have been, 3 rectangles or 5 rectangles. If instead we were looking to eventually find the exact area under the curve, we left the n as an n, and then eventually we let n go to infinity. So then we took the width, which was delta x equals b minus a divided by n, and then we looked at the height of the rectangles. And then again, it just depended. If you were looking at right endpoint rectangles, that was f of x sub I for the height. If it was left endpoint rectangles, it was f of x sub I minus 1. And then what we decided was we didn't want to have to differentiate between the lefts and the rights and the midpoints, so we just left them as x sub I stars when we plugged them into the function, where x sub I star is a sample point. It could be a left endpoint, it could be a right endpoint, it could be anywhere in between x sub I and x sub I minus 1. So when you're looking for the approximate area under the curve, you took the height, which was f of x sub I star, times the width, which was delta x, and that gives you the area of one rectangle, and then you used the summation to add all of those areas together. So that once we wanted the exact area, though, you took that exact same idea. You took the approximate area, and you let the number of rectangles go to infinity. And what we said at the time was this concept of, instead of finding the entire area, you cut it up into infinitely many small pieces and add them together. That concept is going to show up over and over and over again in calculus and physics and in engineering courses. So since mathematicians don't really like to write this big a definition every single time, if it's going to show up often, we like to shorthand things. And that's where your integration symbol comes from. So that's just a reminder of what we were talking about when we looked at area under a curve. So now let's take a look at what that looks like when you apply the same idea to the area between the curves, because believe it or not, area between curves is just about half a step beyond the area under a curve, which we're already familiar with. So the width is found the exact same way. You're looking at dividing your interval from A to B up into n rectangles. If you're looking for an exact area, that's n is going to trend to infinity. If it's an approximate area, then n will be a finite number, like 5 or 10 or a million. So the width stays the same, but it's the height that changes. Notice here, your height of your rectangle actually goes from here to here. The way we find that height is by taking the y value on the top and subtracting from that the y value on the bottom. So for example, if you knew you had a rectangle and the top of the rectangle was at 10 and the bottom of the rectangle was at 3, well, what would the height of that rectangle have to be? It would be 7, because 10 minus 3 is 7. So that's really all there's going to be to the discussion about area between curves instead of the area under a curve. So we're going to divide the region between the two curves into n rectangles with the same width, but now your height is the difference between the function value f of x sub I star and the function value g of x sub I star, which we're going to put some specific requirements on those when we look at the definition. So that your exact area is going to come out to, notice we've got the exact same, you've got the limit notation, you've got adding up all the rectangles, you've got the same width. The difference is here in the height of your rectangles. Other than that, it's the same definition as area under a curve. And so notice when we switch to the integral notation instead of the limit notation, instead of integrating f of x dx, you're going to integrate f of x minus g of x dx. So in other words, when you're looking for the area, and we've got some specific requirements here, the area bounded by curves, you're going to look at y equals f of x and y equals g of x. You're going to look at the lines x equals a and x equals b. So those are the vertical lines on the left side of the interval and the right side of the interval. Assuming you have continuous functions for f and g, and this is assuming that f of x is greater than or equal to g of x for all the x on the interval. Outside the interval, it can do whatever it wants, but this is under the assumption that f of x is the larger of the two functions. If that changes, we will take a look at what happens in that case. So under those conditions, then your area is given by the integral from a to b on f of x minus g of x dx. So let's take a look at some examples. So we're going to find the area of the region bounded above by y equals e to the x, below by y equals x, and on the sides by x equals 0 and x equals 1. So just as kind of forewarning, I pretty much laid this problem out for you. You don't technically need the graph because I told you what's on top, what's on bottom, what's on left, and what's on right. But in general, that's not going to be true. So let's take a look at a picture. So y equals e to the x is the increasing exponential function. It goes through 0, 1, increasing exponential function. And then y equals x is going to be the identity line, right? It goes here. And we're looking at those starting at a value on the left of x equals 0, so that's here, to some value on the right of, let's say, x equals 1. So let's say that's here. So in other words, our region that we're trying to find the area of is sitting right here. So that being said, in order to find the exact area under this curve, all we need to do is integrate from the left side to the right side, so that's 0 to 1. The top function is e to the x, and the bottom function is x. So that's the height times the width of the rectangle, which is dx. Okay, so once we're here, this is really just integration using antiderivatives. So we're using fundamental theorem of calculus here. So the antiderivative of e to the x is e to the x. The antiderivative of x is 1/2 x squared, and we're going to evaluate that 0 to 1. So when you plug 1 in, you get e to the 1, which is e, minus 1/2 times 1 squared, which is going to be 1/2. And then subtract from that. When you plug in 0, you get e to the 0, which is 1, minus 0 squared, which is 0. So in the end, you end up with e minus 3/2. And that's how you're going to want to write your answers. This is the exact answer to the problem. So like I said, this is a pretty straightforward question because I've laid everything out for you. Just know in general, these types of questions don't tell you what's on top and bottom. So let's take a look at some more challenging examples. So we're going to find the area between y equals x squared and y equals 2x minus x squared. So the first thing we're going to do is take a look at a graph, just so that we're sure we have an understanding of what this region looks like. Because notice in this one, nobody told you what's on top, what's on bottom, etc. So you're going to have to figure that out for yourself. So this is y equals x squared. That one's a basic shape. I do expect you to know what that looks like. For y equals 2x minus x squared, I think you can figure out what that looks like. I mean, it is simply a quadratic, so it's a parabola. This one happens to open down, but in general, I want you to be able to use your calculator. I'm not here to test you on whether or not you can graph by hand. You did that in college algebra and pre-calc. So when I put this into a graphing calculator, this is what I got. So the region, notice there is no left and right values given. That's because the only area bounded by both of these curves sits right here. This is the only region that we're going to be looking at in this particular problem. You wouldn't want to look here, for example, because that would also have to be bounded by the x-axis, and there's no mention of the x-axis here. So we need to know the left and the right values. At this point, and at this point. So I don't know, you could use technology to do it. I guess you could use a graphing calculator. This one, the algebra isn't too bad. If you want to know where two things intersect each other, you set them equal. So you take 2x minus x squared and set it equal to x squared. It's just a quadratic, so pull everything to one side, 0 to the other side. So you get 2x squared minus 2x equals 0. Factor out what's common. So you have two x values at the intersections, x equals 0 and x equals 1. So that's going to tell me that my area is given by the integral from 0 to 1. I need the top function minus the bottom function. So on top is the upside down parabola, so that is going to be the 2x minus x squared, and on the bottom is going to be x squared. So this is the integral that I'm going to use. A couple different ways to correctly approach this. I'm going to combine like terms before I integrate. Technically you don't have to though, so if you went straight to antiderivatives, that's okay. When I take the antiderivative of 2x, I get x squared. And when I take the antiderivative of x squared, I get 1/3 x cubed, but I've got a 2 involved in that. So that's 2/3 x cubed. And we're going to evaluate 0 to 1. So when we put in 1, we get 1 minus 2/3. And we put in 0, we simply get 0. So it's 1 minus 2/3, also known as 1/3. That's the solution for this one. So let's take a look at the next one. We're going to find the approximate area of the region bounded by these two functions. So anytime I see that word approximate, I start to get a little nervous in a problem. But let's take a look first at the picture again and see if maybe that explains why we are looking at the approximate value. So when you graph this, and this, especially the first function, the x divided by the square root of x squared plus 1, that you probably really want to get into a graphing calculator. This is actually not that one. This is y equals x to the 4th minus x. And when you graph x divided by the square root of x squared plus 1, it's going to look a little bit more like this, and then kind of like this. So that is your y equals x divided by the square root of x squared plus 1. So the region that we want to take a look at is going to be this region right here. So again, we're going to need to find the left and the right side of that particular region. And this is where the problem is going to come in. I definitely don't want to do this one algebraically. Setting these two functions equal to one another is not going to be a particularly fun equation to solve. So in this case, I would use technology. If you just look up whatever calculator you have on YouTube, if you have a TI-84 or a Casio, whatever calculator you happen to be using, just Google, put it into YouTube, how to find intersections of curves for your calculator, and you'll get a bunch of hits on that. So if you don't know how to do this in your graphing calculator, you're going to want to find that out. But when I put this into a graphing calculator, what I find is that this ordered pair is actually pretty quick. That one's 0, 0. This one, I actually didn't write down the y value. I just wrote down the x value. The x value was approximately 1.18. And that's where the word approximate is going to come in. I didn't find exactly where the right-hand side of this interval ends. And that's why technically my area is only going to be an approximation. So when we go to set up our integral, area is going to be approximately, you're going to go 0 to 1.18. And then you need the top function minus the bottom function. So that is going to be the x divided by the square root of x squared plus 1. And then you're going to subtract from that, be a little careful here, you're going to subtract from that x to the 4th minus x. But if you write it like this, if you write it like this, the problem is you're not subtracting the entire function, you're only subtracting the x to the 4th. So you're going to want to put parentheses around that whole thing, or just distribute the negative, whichever one. So that's the setup. Now we have to actually figure out how to integrate this one. And if you concentrate on the x to the fourth minus x, that's just straight up antiderivatives. That's not too big a deal. That first term, however, you're going to need to integrate x divided by the square root of x squared plus 1. And if you remember from section 5.5, that's a u substitution. So the first thing I'm actually going to do is I am going to split that into two separate integrals since I have two separate techniques. So I have the integral from 0 to 1.18 of x over the square root of x squared plus 1 dx, and then minus, because that's the sign we have there, integral 0 1.18 of x to the fourth minus x dx. Okay, so let's go ahead and do the u substitution. For the first integral. If we let u equal x squared plus 1, then du is going to be 2x dx, so that 1/2 du is my replacement for x dx. So when we go to work with this integral, we end up with the integral of x dx here gets replaced with 1/2 du. And then we have the square root function does not get replaced. It's still there. And in place of x squared plus 1, we have u. So those are in the denominator, so you get 1 over. The other thing you've got to be careful of is this is a definite integral using u substitution. So you've got to change your limits of integration as well. When x is 0, I'm going back to this relationship right here. If x is 0, u is 1. If x is 1.18. I took 1.18, I squared it, and then I added 1, and that got me 2.39. Okay, so that's that integral, and then I'm going to go ahead and just do the second one. It's antiderivative, so it's 1/5 x to the fifth minus 1/2 x squared, and that's going to go 0 to 1. Okay, so pardon me, I have to continue down here. So we're going to get 1/2 times. This particular integral is technically, it's u to the negative 1/2 power. So when you go ahead and take its antiderivative, what you're going to get is u to the new power of positive 1/2. And then in front of that, you're going to get the reciprocal of the new power, which is 1 over 1/2, which is 2. So you're going to get 2 times u to the 1/2. That's going to go from 1 to 2.39, and then you're going to get minus 1/5 x to the fifth minus 1/2 x squared, but since those are x values, those stay with the 0 and the 1.18. Okay, so when you clean up all of that, I'll write some of the calculations down. The 1/2 and the 2 cancel. You get the square root of 2.39 minus the square root of 1, which is of course 1. Minus, you get 1/5 times 1.18 to the fifth power minus 1/2 times 1.18 squared. When you plug in 0, it zeroes out both terms. What I got when I got done doing that was approximately 0.785. And that's the approximate area for this one. So I did promise you that I would take a look at what happens when the function that is the larger function isn't the larger function for the entire interval. So what happens when that occurs? So this is a picture, for example. You're still integrating from A to B. So you need the entire area from here to here. But notice which function is on top changes. So how do you think you're going to address that? You're going to split your region into multiple smaller regions, and then you're going to take the area from here, from the first region, add it to the area from the second region, and add it to the area from the third region in this case. Sometimes there'll only be 2 regions, sometimes, I mean, in theory there could be as many as you wanted, but you just add them all up. So you'll have to split it up. You're often going to see that written as the integral from a to b of the absolute value of f of x minus g of x. The reason you see that is because absolute value is, of course, a piecewise defined function. Sometimes it's f of x minus g of x, sometimes it's g of x minus f of x, depending on which of the two is larger, and that's exactly what we're talking about here. So let's take a look at an example. We're going to find the area of the region bounded by the curves y equals sine x, y equals cosine x equals 0, and x equals pi over 2. So when we look at the graphs, remember cosine x is your even function. So that one hits the y-axis at 1, and then by the time it gets to pi over 2, it's down to 0. Of course, this continues farther in both directions, but I'm really just looking between x equals 0 and x equals pi over 2. Your sine function starts at 0, and by the time it gets to pi over 2, it's up here at 1. So it essentially does this. And then we're going to also look at this in between the vertical lines x equals 0, which is the y-axis, and x equals pi over 2, which is here. So what you really want to do, I'm going to pause for just a second. I want you to look at this graph, and I want you to, in your mind, get your eyes on which regions you think you're supposed to be finding the area of. Got it? Keep in mind, you're only looking for the regions bounded by sine x and cosine x, and then the two vertical lines. That's here and here. Those are your two regions. You are not looking for the area in that particular region, because the area in that region would also have to be bounded by the x-axis, or y equals 0. So we are not dealing with that one. So as you can see, if you look at the two regions, in the left region, the cosine function is on top, and in the right region, the sine function is on top. So I am going to have to split this. So the area in this case, I need to know the x value here, because it's going to determine the right side of the first region and the left side of the second region. So what you want to think about is, when are sine x and cosine x equal to each other? And that's at x equals pi over 4. That's a unit circle question. So we're going to have two integrals. The first one's going to go 0 to pi over 4, and that one has cosine x on top. Second one, minus sine x dx. And then we're going to add the area from the second region. So that one's going to go pi over 4 to pi over 2. In that region, though, it's sine x on top and cosine x on the bottom. Okay? So we look at antiderivative. So the antiderivative for cosine x is sine x. The antiderivative for sine x is negative cosine x. Because there's already negative there, this will go plus 0 to pi over 4. And then plus. And then again, the antiderivative for sine x is negative cosine x. Oops, I wrote the wrong thing. Negative cosine x. And then the antiderivative for cosine x is sine x. There's still a minus there. Minus sine x. And that's going to go pi over 4 to pi over 2. Okay. So when we plug in pi over 4, the sine at pi over 4 is 1 over the square root of 2. Same thing at cosine. So plus 1 over the square root of 2. Minus the sine at 0 is 0. The cosine at 0 is going to be 1. So keep in mind there's a parenthesis here. So technically that's a minus 1 when we're done with it. Plus, when we plug in the pi over 2, the cosine at pi over 2 is 0. So that's kind of a negative 0, but not really. Minus the sine at pi over 2 is 1. And then we're going to subtract from that when you take the negative 1 over square root 2 when you plug in pi over 4, minus 1 over square root 2 when you plug in pi over 4 to the sine function. So what we get is, that's 1, 2, this one's a plus, the next one's a plus, so that's 1, 2, 3, 4, 4 over the square root of 2. And then we're going to do, let's see, that's minus 1, so minus 2. You can leave it like that, or you can rationalize the denominator, in which case that's 2 root 2 minus 2. And again, that's fine. I would also take 2 times square root of 2 minus 1. Any of these are fine. What you need to have are exact answers, but they can be equivalent. I don't care which of those three you have, as long as it's an exact answer, meaning no decimals. So then the next thing that we need to take a look at, before we get to it, I want to ask you an old question. is y equals x squared a function? This is a question you've probably heard many, many, many times, starting in intermediate algebra, college algebra, pre-calculus algebra, and it's a little bit of a misleading question. I mean, usually the answer you get is y equals x squared. Yeah, if you look at the graph, it looks like this. It passes vertical line test, so it's a function. And then if you take a look at is x equals y squared a function, a lot of students will tell you, okay, well, it is a parabola, but this is an open right parabola. It fails vertical line test, and therefore it's not a function. It's just, if somebody asks you this question, it's not quite a precise enough question, because technically this is a function. If you're referring to a function of x, and if you're referring to a function of x, this one is definitely not a function. But, this one is definitely not a function. But what if instead of saying, is it a function, what if I said, is it a function of y? Meaning for each input of y, there is a unique output of x. And the answer is yes, it's absolutely a function of y. So the trick with these is to know which type of function you are supposed to be looking at. So this one is referred to y is a function of x. It's the one we're most used to discussing. This one is a function if you're willing to say that x is a function of y. Okay, so it's all about your solving for x in terms of y. It's a function. If you had something like x squared plus y squared equals 16, that is neither a function of x nor a function of y. You can't solve for x or for y using a single equation. Okay, of course, if you solved for something like y, you'd have that plus or minus thing going on. And that's why you wouldn't be getting this as a function. The same thing would happen if you tried to solve for x. So the reason that this is going to come up, the reason we're talking about this at the moment, is because sometimes there are some regions that we're going to take a look at, not just in this section, but as we move through some of the other sections in calculus, that it's going to be actually in your best interest to treat the region as a function of y instead of as a function of x. So for example, I didn't give you equations to describe these, but you can clearly see that if you look at the red line here, that is, excuse me, not a line, the red curve there, that is a function of y, not a function of x. And this one is also a function of y, not a function of x. So when you look at attempting to find the area of that region, if you try and make your rectangles go in this direction, you've got some problems, right? That would be really not what we end up talking about. It makes it so that you've got different heights, you've got different functions determining your height depending on where you are in the interval. So for example, here, this height would be determined by the blue line. Here, your height would be determined by the straight line. Here, the height would be determined by the red line. We really do not want to have to mix all of these up, pardon me. We really don't want to have to mix all of these up. So it's actually in our best interest to kind of look at this from a slightly different point of view. So if you take a look at the rectangle that they have drawn in for you, if your rectangles go the other direction, notice your height is always determined by the red if the rectangles are going in the other direction. And then the bottom, because this is between curves, not under a curve, the bottom of your rectangles are always determined by the blue curve. Okay, so we want to take advantage of this. Now what that's going to change though is, notice this is now our this is now our interval from here to here. And all of our widths, all of our rectangles are going this way. Our width is no longer a delta x. Our width is now delta y. Okay, and that's going to make a difference when we go to talk about our integral. So if a region is bounded by curves with equations x equals a function of y and x equals a function g of y equals c, which is the horizontal line on the bottom this time, and y equals d, which is the horizontal line on the top, f and g have to be continuous. And again, we're assuming that f is larger than g. Now in this orientation though, larger doesn't mean on top. Larger means to the right, because that's where our larger values are. for all the x values on that interval, then the area is now given by f of y minus g of y. And because of the fact that this is a delta y, that means your integral is now with respect to y. But that's a good thing because your functions are with respect to y. You actually want it to work out that way. So let's take a look at an example. Find the area enclosed by the line y equals x minus 1 and y squared equals 2x plus 6. So again, first we're going to get an eye on the graph and what does this look like. So y equals x minus 1, that one's pretty straightforward. That's just a line. It's got a y-intercept of -1 and a slope of 1. The other one is an open right parabola. It's actually shifted by 3 to the left. If you're not sure what that looks like, you can either solve for y using plus or minus the square root of 2x plus 6, or if you've got Desmos, something like that, you can put it straight in. But basically your graph, here is the parabola, and then your line is going to do, it's going to go through -1, so it's going to do essentially this. So the region that you want that's enclosed between those two curves is sitting here. So this time what we want is the right function minus the left function, because if you tried to deal with this as a function of x, look at your rectangles, okay? Your rectangles are going to go, let's say, here's one height of a rectangle, here's a height of a rectangle. And if you look at those two, notice this one, the first one, it's bounded between the upper and lower halves of the parabola. And if you switch to a different rectangle, say over here, the top is still the upper half of the parabola, but the bottom is bounded by the line. You'd have to break this up into two separate regions and look at region 1 and region 2. And while that's not wrong, it's really not particularly easy in some cases. So instead, we're going to make it so that our rectangles have the other orientation. They're going to go this way, because look at the heights. If you go this way, they are always going to have the green line on top and the red function underneath, with the understanding that that function is not a function of x, it's a function of y. So my area is going to be with respect to y. I need the right side, the green line. Now I'd like to tell you that you can just write x minus 1 here. You can't, because remember, this integral is going to be with respect to y, which means everything you write here has to be in terms of y. You can't write x's here. So the good news is that's actually a really easy fix. You just take your line, solve it for x instead of for y. So x is y plus 1. So that's what we're going to put there instead. So we're going to use y plus 1 as the larger of the two functions, meaning it's on the right, and we're going to subtract from that the smaller of the two functions, which is the parabola, and we're going to run into the same thing. You can't write it as 2x plus 6. Everything needs to be in terms of y. So we're going to solve this for x. So when you look at this one, you say that y squared minus 6 is equal to 2x, so that if you divide by 2, it's 1/2 times y squared minus 6 equals x. Okay, so you can write that a few different ways. I'll go with 1/2 y squared and then 3. Now, technically, from the solving of x, this is minus 3, but keep in mind that negative needs to apply to both of the terms that follow. So either stick some parentheses in here or understand that that's actually plus 3 because of the distribution of the negative. So that's the larger function minus the smaller function. The other difference is you got to watch your limits of integration. Everything is with respect to y. So we're not looking from the left side of the region to the right side of the region. It's the top of the region. Remember, that's the y values here to here. You're now bounded on the top and bottom. So we want the y values, the largest y value for the region and the smallest y value for the region. And again, in the interest of time, this ordered pair is 5, 4. This ordered pair is -1 -2. So my y values that I'm going to use for my limits of integration go from a lower of -2 to an upper of 4. Okay, so that's the setup. From here, it's really just a matter of doing the integration, and this one is completely just antiderivatives. I can go ahead and combine like terms first if I'd like. So I have, I'm going to reorder, -1/2 y squared, we'll have a plus y, and then we have a +1 + 3 for +4. If you didn't combine like terms and went straight to antiderivative, you're going to come out to the same thing I am. So then I go ahead and do antiderivatives. So I get -1/6 y cubed plus 1/2 y squared plus 4y, and we go -2 to 4. So at this point, I'm going to assume you know how to plug in the 4 and subtract from that what you get when you plug in -2, and the resulting value should come out to be 18. So that's how you deal with it when you want those rectangles to go in the other orientation. And this is something that's going to come up not just here, but in other sections. So make sure you're good with this type of example.